Good afternoon, everyone. For our 413 modeling project, we decided to pick McDonald's. So why did we choose McDonald's? McDonald's implements queues for their customers when they come and order meals. So what was our project's problem statement? We wanted to find the optimal staffing for the cashier and kitchen staff to keep the queue under 5 people at all times.
For the McDonald on green we are simulating, there are 5 entities: the cashier, the kitchen staff, the cleaning staff, the service table, and there is also one guy just for inventory checking in. And the policy and law for this store is it open 24/7, and this the position can be transferred for all the staff there. So for the simulation, we made 2 different versions. The one above is the one pretty similar to the real world, where the manager can transfer the staff from the position of the kitchen to the cashier, but that's far too complicated and far too it's not really good for analysis. So we simplified the version into just having the cashier and the kitchen inside, and the customer distribution we have is inhomogeneous Poisson distribution, and the server rate for both cashier and the kitchen are normal distribution.
So now we want to run the simulation that was just mentioned, and we want to optimize the number of the server size, which is the cashier size, and the kitchen size for 2 cases. One being for the weekend and one being for the weekdays. For the weekend, we want to first look at the customer distribution, and as you see from the left diagram, you see that from 1 a.m. till 10 a.m. the customers are barely coming to the restaurant. However, from 10 a.m. to 1 a.m. there are a lot of customers coming to the restaurant, as you can see from the higher bars in the graph. Therefore, we want to first optimize our number of cashiers, and we first start with size 1. And when we run the simulation based on that, we see in the figure on the right side where we can see the queue is always below 5 customers. So we can therefore conclude that our optimal size for cashiers can just be 1. Now we want to optimize the number of the kitchen size staff, and we start from size 1 as we did for the cashiers. However, for this time when we run the simulation, we see that the queue size exceeds the 5 shortly after some time, and therefore we cannot assign just one person for the kitchen, as it will be too inefficient. Therefore, we want to increase the size, and we wanted to first increase the size to 3 because we know that the service rate of the kitchen staff is approximately 3 times slower than the cashier's rate. Therefore, we increase the size of the kitchen staff to be 3, and when we run the simulation, we see that the queue is always under 5, which makes the solution acceptable. However, we want to also try to run another simulation with size 2, just in case if it is optimal or not. And when we do so, we still observe a similar pattern to before, where the customers are always 5 or below throughout the whole simulation run. And so in order to save more money, we decide to optimize this number of kitchen staff size to be 2. Overall, for the weekends, therefore we can say that the optimal number for the cashier can be just 1, and optimal number for the kitchen staff can be just 2.
Since the weekday and weekends have different customer distributions, we ran different simulations for the weekday. So, as you can see from this customer distribution, this is what we used for our weekday analysis. With this customer distribution, we ran our model. We ran it with determining the queue sizes for 1 versus 2 cashiers. From the diagram on the left, you can see the queue size for having 1 cashier. Based on this, we determined that having 1 cashier was not optimal because we had queue sizes greater than 5. On the right, you see the queue size for having 2 cashiers. When we see this, we see that we have queue size less than 5 customers. Therefore, we determined that for the weekday, the optimal allocation for cashiers is 2. Now, we have to determine the optimal kitchen staff size. Based on the ratio we had for the weekend, we found that having 2 kitchen staff to every 1 cashier is optimal. So, since we determined that 2 was the optimal cashier size, we ran a model for having 4 kitchen staff. And you can see this on the left side. There was one instance where we had 6 people in the queue when we had the staffing of 4. And on the right side, we see the simulation run for having 5 staff in the kitchen. At this instance, everything was under 5 in the queue. But we determined that the optimal staffing size is 4 since it's not cost efficient to have 1 more staff allocated to just reduce 1 instance when we only had 6 in the line. So, in conclusion, we found that the optimal staffing for the cashier is 2, and the optimal staffing for the kitchen staff is 4. Based on these quotas, we were able to keep the line under 5 at all times.
So from our result, there were some possible errors that can be detected and has to be considered from our project. Since we got the data from Google Live that counts the customers from using the GPS near the area, it is not the exact actual customers who were using McDonald's in the Green Street. To estimate the actual data, we picked 3 o'clock in the afternoon for half an hour and count the customers and estimated the customer distribution in the base of the count. But still, it is not representative for the actual customer distribution. Considering the customer distribution is sensitive to the season in our university life, our result could only apply for school year. Also, there is no initial data since McDonald during the school year runs 24 hours period, which means there is no transient state for this model that we made. However, it could be acceptable for producing a rough schedule. Since the data we have are not official data, the analysis we made is simplified version of the actual real system. All the possible variables could come out in the real system, such as possible waiting time for deciding order or possible duration time of the tables. After the simulation model, we found that the best server size ratio of cashier and kitchen would be 2. In the real system, there are chances the queue go over 5 with the ratio of 2. We would not recommend the manager to add 1 more server. But what he could do is to transfer the servers between the cashier and kitchen to solve these problems. With the inhomogeneous customer distribution, we have total 2 different shifts in the weekends and 4 shifts for weekdays as shown in the table below. As shown in the table, all the server number matches with the actual staff number, and it concludes that our system works regardless of all those simplifications.